And then we're moving in another very exciting session from quantum computing to quantum communication. Noel Goddard, welcome to the WOMANIUM Global Quantum Program. Excited to have you speak.
Thank you. It's such a pleasure to be here.
Great. Your audio, everything works well. We're excited to have you. You started as a professor in physics at Hunter College, but then soon took the entrepreneurial road. You started a food safety diagnostics company. Then Noel Goddard started a startup company on oral drug delivery of cellular and biological therapeutics. Now moved to the quantum space, and you are the CEO of Qunnect. Could you share more about Qunnect?
Sure. So thank you for the introduction. I was thinking how funny it must sound to have the biology background that then becomes the quantum background. So I was part of there were these interface programs that were in the late 90s, where if you were majoring in physics and you wanted to do something interdisciplinary, they often had these programs where you would take all of your physics courses and all of your other courses, whether it was chemistry or biology or whatever, together, so that you basically just had two tracks rather than the sort of more streamlined combined degrees that they have now. So I started off as a condensed matter physicist that did a lot of optics and a lot of instrument building. And condensed matter physics aligns very closely with a lot of fun stuff that happens in biophysics. So I did most of my research in biophysics and built the biophysics program at Hunter College. And then I was interested in jumping out to do stuff in the entrepreneurial realm, just because New York City was starting to finally have some facilities that were reasonable rent to be able to do these things. But I had postdoced in George Church's lab, who's on more companies than I think I can count in terms of spinouts and boards. So he's at Harvard Medical School, has done a lot of amazing things. So I was always exposed to it, I just hadn't done it yet. And then I met Qunnect because as I was doing these biological companies, I was searching for funding like everybody does. And I had met some people from New York State who were putting together a economic development fund that would specifically support young companies that were raising their first funds if they had very rich IP assets, so intellectual property assets. That's kind of another way of saying a direct university spin out, but they didn't have to be from a university. The ideas of the companies is that they built stuff, whether that be biological stuff, robotics, other types of electronics, clean tech, sort of hardware. We didn't do much software. And that was something that was decided by the fund largely because in New York State, software opportunities get funded all the time. So in the last part of me being at Qunnect, being at the state fund, I met Qunnect because they were looking for their first funding. And everybody that we accepted into the program, we ended up mentoring. So that's how we ended up actually being invited by their founding team to come and be part of their management structure. And it was fun. Obviously, it was a different part of physics than what I spent my graduate school and my research career in. But physics is physics. That's one of the most beautiful parts about it. So, yeah, so it was fun to get back to it. so that's a little bit about me. Now let me just share my screen and I'll tell you some about Qunnect. Are you seeing my screen okay?
Yes, not a full view yet.
Okay, great.
Excellent. Please go ahead.
So Qunnect is a quantum networking company, and I know you just heard from Marlou about quantum computing, so this is another vertical in the quantum technology space. I entitled today's talk, Quantum Networking, the Practical Distribution of Useful Information, because I think it's very important to start thinking about what we do with quantum. Qunnect's real mission is building instrumentation which can actually function in the existing communications infrastructure, which is all the telecom fiber that exists here today. And it's a different way of coming at the problem than coming at it from a pure academic sense. There are a lot of opportunities to do very beautiful quantum networking type experiments in laboratories, but the moment that you try to take them out into an industrial environment or deploy them in the field, you have to start thinking about different types of engineering challenges. So just to dissect this sentence a little bit, when I say the practical distribution, what I'm talking about is instrumentation that can come out of the lab and be in the field, and instrumentation that can scale. So if you want to build a network, you want to be able to deploy instrumentation every 25 to 50 kilometers. That's a lot of units. And if you're talking about a refrigeration unit that needs a few $1,000,000 every 25 to 50 kilometers, that's a hard prospect for being able to build a network. It also needs to be compatible with telecom infrastructure. A lot of quantum doesn't happen at telecom wavelengths. So it's something that has to go into your design piece. When I talk about useful entanglement, there are all types of qubits. So traditionally, when we start talking about qubits that are used for communication, oftentimes we're talking time bin qubits because traditionally they were easier to use and were less affected by the environment. The problem is they can only be used for communication and can't be used for other things. So it would be great if we could learn to use different types of qubits within the telecom infrastructure that can interface with quantum sensors and quantum computers, because the long-term vision for all of this is that we have something analogous to our existing internet by connecting quantum devices over quantum channels. And then finally, long distances. So one of the challenges if you're going to start communicating with single photons is that you need to be very aware of fiber transmission losses. So there's no really analogous process, in the digital communications world. You send bursts of light through fiber. You have the option to clean them up and to amplify them at any time. That's not something you can do in quantum. So that process of repeating can be done in quantum through a different type of process that I'll mention. But that's the only way you can start having long distance networks that start to emulate the same type of infrastructure that we have now for digital networks. So the evolution of quantum communications out of digital communications, right, is highlighted on this slide. So again, for digital information, they're carried in pulses of light or little bursts of light. Typically, those light pulses are mathematically encrypted to equal some type of message or key. And the application today using digital networks is secure communication. What's different about quantum is that instead of bursts of light, now you use single photons of light, and you choose one of the quantum states of those photons in order to be the information itself. So now the information is physically encrypted in the light particle, and the application of that is super or ultra secure communication because it follows all the rules of quantum mechanics. It makes it extremely sensitive to being able to detect hacks. And then, of course, the future vision is that this is going to grow from being something which is just used for communication into something that actually hosts quantum sensors and other quantum devices like computers, et cetera, where you can do distributed sensing or distributed computing over long distances. And in terms of technology evolution, the first generation of quantum communications to use single photons is called QKD. Europe has chosen to follow a widespread QKD strategy through the EuroQCI to make QKD networks in every one of their member states. The US has not been so positive about QKD, but China implemented a very large QKD network across their country and also with the ground satellite link some years ago. So that hardware exists. People are learning a lot about deploying and communicating with single photons for those types of protocols through what I would call a first generation tech. Our technology is different because instead of using a point-to-point encoded single photon for communications, we're actually trying to distribute entangled photons and use those for communications. So that field is kind of a second generation of quantum communication and holds the promise, of course, to be the underpinnings of the quantum internet. And we call it entanglement distribution networking. There are a number of companies involved in this. If I showed you this chart like as few as 2 years ago, it would be 1/3 the size. So companies are jumping in at the software side. So there's an American company called Aliro who works on control of quantum networks over the quantum internet. There are also very large players, like Marlou was mentioning earlier, for quantum computing. AWS is also in the world of quantum communications. They recently announced a partnership with De Beers, the diamond company, and Harvard in order to roll out some of their stuff. And in fact, I just saw an article in Popular Science if you want to read more about what they do. NuCrypt is a slightly older company that came out of Northwestern. Bohr Quantum came out of Caltech. Qubitek came out of Oak Ridge National Labs. QNet came out of MIT and University of Arizona, and WeLink is out of professors at Sorbonne. So all of these are academic groups which transition into spinning out different types of technologies. And one of the technologies which is critical to thinking about how we actually build more complicated networks is having a quantum memory. So several of these companies have quantum memory technologies which they use at their core. Others are focused on short distance networks where quantum memories are not necessary in order to get some better performance. So stay tuned, but there's a lot of interesting and fast stuff happening in the field. And this is how entanglement distribution networking works. So it's based on a concept which actually was part of the 2023 Nobel Prize in Physics. So entanglement swapping is an underlying protocol that happens at each elementary link, and this is what an elementary link looks like. You have two entanglement sources, which are shown with the little infinity sign icons there, which produce a pair of photons. And in Qunnect's case, these are two different colored photons. You send one half of the photons to a middling node while you store the other half of the photons in quantum memories locally. At the middling node, you interfere these, and then when you do that, you actually end up mapping the entanglement of the two remaining photons in the memories onto the same state. So you've gained the distance between the two outer nodes, and you can do that again in another elementary node, so that you have two elementary nodes who are separately entangled. And then you can have a middling node on a different layer of architecture from that, where you release the two photons from the center memories, interfere them there, and now you actually have spread your entanglement state from the far distance of the left node to the right node. So this is the basis of how an entanglement distribution network would work. And Qunnect is building those products which are in those boxes. So we're very proud of the fact that in September of 2021, we built the first commercial memory on the market worldwide. Our memory is very unique because it operates at room temperature. It does not require any cryogenics nor any high vacuum in order to function. If you'd like to read more, we have a PhysRev applied paper. It's also on the archive. You also need good photons to be able to make a network work. So we built an entanglement source, which is compatible both with telecom infrastructure and with our memory. That paper is also posted on the archive. It's one of our more recent postings and it's been submitted for review. And one of the special things about our source is that it produces photons which have very narrow line width. So we use a spontaneous four-wave mixing process, which is a little different than the other commercial sources on the market. The photons which come from the source are sort of naturally at a few hundred megahertz in line width. And we're able at this point to produce 10 million polarization entangled pairs per second, which is a very admirable rate, especially for atomic sources. And then in order to have that interference station, you need to have a place where you can do a Bell state measurement. We've been playing around with a bunch of different designs, so we don't offer this commercially yet, but it's still under development. We've sold 4 memories to date. We're about to deliver the 5th one. We just sold our first entanglement source as well. But one of the problems is that quantum products for that nice little cartoon are not enough to work in the real world. I've already mentioned the temperature and vacuum situation. The cryogenics in terms of scalability are hard. Every other memory technology that's being used by all of the competing companies on that early slide require cooling their technologies down to millikelvin, which of course requires very serious refrigeration. We think that a future quantum network will probably be a hybrid of some of those cold technologies because there's certainly a lot of advantages of the cold technologies and technologies like ours, where we could be the links that are between all of some of these more fancy sort of end nodes. But one thing which is very tough about quantum is that the instruments need to be low maintenance and stable. That's very difficult to do because if you run a quantum laboratory and you go in, you see that graduate students are tuning instruments all the time. You want something which you can build, deploy at scale, and not have to touch any further. And that's particularly true in terms of fiber hubs. So, the security to be able to have access to those fiber hubs is typically quite high. So that's something that really informs our design strategy. Also, instrument and instrument to network interface losses become very big. Quantum instruments don't talk to each other really well, and that's one of the reasons that we built our own source, was to start thinking about optimizing interfacial losses between instruments and also towards the telecom fiber infrastructure. Of course, telecom fiber is deployed already, and it's subject to lots of environmental perturbations, so you need to figure out how to deal with that as well. And then finally, the precision of quantum instruments really demands that we have highly precise local references in order to be able to drive all of this stuff. So we then built a second product suite of support instruments that sit at every one of these nodes. So those are the things not in boxes. And Several of them are commercially available. So this quantum autopolarization compensator is a set of boxes that flank any piece of fiber you're sending quantum information through and sends out a test signal consistently onto the lines in order to calibrate the real-time noise and drift so that you can correct for it. And then it applies that correction signal to all the quantum information which follows the calibration cycle. QLock is a really cute little instrument that we built to be able to stabilize the lasers that drive the entanglement source. We've been able to do this for many days at a time. I'll show you that in the next piece of data. Then, of course, you need a very accurate timing reference. All of these things about moving photons from one place to another need to happen with sub-nanosecond resolution. So we've been working on the electronics to be able to control all of that. And of course, the end goal is it all sits in racks, and those racks sit in fiber hubs. So that's what we engineer for. And in the meantime, Qunnect built a test bed in New York City. So this was the joining together of lots of different segments of dark fiber that pre-existed. So they were in existing cables within the ground. We had a commercial fiber company fuse them to each other so that we could have a fiber test bed in New York. So Qunnect sits on the edge of Brooklyn. We have a set of fibers that run through Brooklyn and Queens, which is 34 kilometers to the right of the company. And then another set of fibers that run from our facility all the way into Manhattan and terminate at NYU's Center for Quantum Information Physics. That set of fibers is particularly interesting to us because it's going to be the first time that we measure things which are under any type of water body, which of course in New York, that river that it flows under has a tremendous amount of boat traffic and ferry traffic. So that will be interesting. But our very first sort of thing to prove is that we could use polarization qubits for communications. So we needed to be able to prove that we could have high rate preservation of high quality polarization qubits over this 34-kilometer loop, which you see here. And we have in fact completed that. Our next steps are then take 2 loops and do entanglement swapping, which is the process that I showed you in the animation. And then also we want to be able to show that we can now deliver these polarization qubits across the river to NYU as well, because things become different whenever you're not working in loops and you're working in 2 physically different locations. So we're hoping to have all of those things done by the end of 2023 and then some exciting stuff in 2024. This is a snapshot of the dashboard of what we do on our communications network right now. So we actively track the photons that we're putting into the network and how well they come out of the network. So the S value is something that you calculate based on receiving a pair of photons where you can see if they're still entangled. So that's through a CHSH measurement. The QBER is the quantum bit error rate, which is how different what you receive is from what you sent. So if you want to be able to have accurate communications, that can't be very high because you want to know what you're actually sending. So our real-time stats right now are that we inject about 4 million pairs a second into the telecom fiber network that we have. It's actually half of the pair because it's the telecom side. Of that, 130,000 of those survive and are usable for the CHSH measurements. And when we do this, we are able to maintain an S value of 2.7, which is almost as high as you can get. 2.8 is the actual physical limit. And due to that instrument that I showed you that's able to do calibration of the different fibers, we're able to maintain a quantum bit error rate at less than 2.5%. While having 95% fidelity on the channel itself and with 99% channel uptime. So those numbers start to sound like a real communications network, as opposed to something that you just see in the lab and you make it work long enough in order to just get an academic paper out. So we're very proud of this, and we think it bodes very well for our next experiment to actually do the entanglement swapping procedure. The network itself is wildly stable. So the QAPC and the QLock maintain that fidelity over very long time periods. In this dashboard, you're seeing 6 hours here, but you can see how it walks around and it's corrected in the fidelity part of the channel. We can run it as long as we want. The longest thing that we've done so far is 7 days. And over those 7 days, we also had very good stabilization of our lasers. So stay tuned. Hopefully some exciting stuff coming up. To put this in perspective, there are other groups worldwide who have tried to distribute entanglement over long fibers. The vast majority chose to calibrate their fibers before they started to do their data runs, and then they just used their fibers until the error rates became so high that it wasn't practical anymore. We actively correct, so that's why in the bottom here we've got 99% channel uptime for more than 7 days at a time if we want it. The others have a problem that their error rate increases over time as the polarization drift starts to get higher. But something that we're very proud of is that we're sending 130,000 pairs a second into our network, which is significantly higher than anything else that you see here, which has been done previously. You have to have a lot of photons because you have to be able to afford losing some of those in order to have real communications protocols. And of course, we're operating at very low Q/ber and good S values. So long-term vision is that if you want to be able to do something useful, you want to be able to connect these things to also quantum sensors, quantum computers, or you want to be able to send messages. That's when you cross from the domain of entanglement swapping, which helps you basically build your channel, to sending information, which you would do through a process like teleportation. So there's a very good archive paper that came out recently, a Hertz rate metropolitan teleportation from one of the Chinese groups. It has within it this nice table where they've compiled all of the different papers which have done teleportation over different distances and the associated rates, some of them in fiber, some in free space. We're hopeful that having the very high rates that we have on our network right now means we're going to beat some of these rates. So that's one of the things that we plan to do in 2024. But it's extremely exciting to see that there are this many examples that we can even, again, technology happens because people are evolving it. So the fact that there are all of these other interesting pieces of work out there right now will be something that we can use as an archival base to learn from their mistakes and continue to push forward. We're hoping, of course, that our rates will be something closer to maybe 25 Hertz or better, which is still not breaking any like speed records, but speed records for the teleportation world. So I hope that next time I get a chance to present to this group, we can give you some of that data too. So this is where we work. This is the Brooklyn Navy Yard. We first established a 1,500 square foot facility in the end of the pandemic, so July of 2020. So all of the work that I presented to you is stuff that's happened in the last 3.5 years as our team has grown from 3 people to 16 people. We just established a 4,000 square foot lab space on the other side of the Brooklyn Navy Yard to turn our original space into a network hub and our new space into an R&D space. There's a nice picture of us on Quantum Day this year. So very proud of our team and everything that they've done. I've put the little pink arrows there to highlight the fact that of the 16 team members I have, 5 of us are women. So I just want to say that it is a diverse company. We're proud of the fact that it is. And we have a number of people who identify as non-white. So I think we're diverse in 2 different axes. And that's it. So are there any questions?
There are many, many questions. Very exciting, and also really exciting how fast the developments have been the past years. I would like to combine a couple of questions. Lulari asks, what do you think will be the first real-world application of quantum networks? And then Ayush from India asks, how can quantum networking be useful in sending or receiving signals on large distances, like from Earth to the moon? How is it better than classical networking?
Both good questions. So I think Worley had this statement at the end, because I was at the very end of your questioning session, where he compared the technology of quantum computing today to something in the 60s. It's actually very relevant for thinking about quantum communications as well. So something that I think we forget because of the conveniences of being able to stream large amounts of information over our cell phones is that it actually took 20 years to go from the first hardware, the first protocols, and the first infrastructure of the digital networks to something that we use routinely like TCP/IP. And it would still be a couple of years before the World Wide Web would come on top of that. I think we all have, and that's with a lot of very smart people, all applied to the exact same problem. So as much as we like to say that things evolve differently in the technology space today as versus then, I think we also have to be patient for the fact that some things will be revealed as the technology matures. For the moment, quantum communications has exceptionally high security, but is very slow. And this dictates what the applications will be. So right now, anything you can afford to send slowly but needs high security is the application. And those applications tend to be keys. So there are examples of having done quantum communications over satellite to ground links. China put a satellite into orbit in 2016 called Messius, which has an entanglement source in it. So it beams, paraphotons down to ground stations. Because it does that, they were able to link 2 different points across China as a proof of concept that you could send a key between the 2. And then they actually also were able to link to a laboratory in Austria, where they were also able to show, again, secure communication of a key. And then the key is used to do something else. So I think that will be the first application because it is the most natural one given the speed problems. Why is it better? Well, it depends on the type of communication you're trying to do. So again, if you really want to do something securely, which is obviously of interest to the Defense Department, it's of interest to finance, it's of interest to critical infrastructure, those are the first users. And then hopefully it will come into some niche markets of people who need higher security for things that telecom service providers might be able to provide.
Regarding security, could you share more about quantum internet versus post-quantum cryptography, about which we will have a talk on Friday?
So I think that, again, this goes back to the idea of physical encryption versus mathematical encryption. I think we all know that there's an existential threat that the quantum computers are going to break all of the existing mathematical algorithms, including PQC. I think one of the sad sort of stories in the PQC universe is that people could break some of these things on laptops, right? So everybody's a little worried that PQC is sort of a band-aid, not a solution. The quantum internet holds the promise, and again, I will say holds the promise rather than solves, because I think it's arrogant to believe that we're ever going to get beyond the hacking problem, but it has the promise to be able to allow, physically secure encryption between its 2 entities. Quantum physics tells us that we should be able to know when the eavesdropper is on the line, basically instantaneously, if we make the right snoop detectors. It doesn't prevent someone from hacking, but it should prevent some of the harvesting problems that we see right now, where someone doesn't know the hacker's on the system for 9 months. So the idea is, I think, hypersensitive detection of hack versus hack proof. It often gets advertised as hack proof because, well, that sells headlines.
Great. Now there is a workforce related question. Satyam asks, how do you think theoreticians fit in this time where we also see an increase of the need to bring technology to practice?
Mm-hmm. Great question. It's interesting. So JP Morgan has the banking system has a large quantum group in New York City. Goldman Sachs used to have one, Wells Fargo had one. I mean, so there are all of these banking entities that hired quantum physicists. Almost always they hire theorists because there's banks don't want to build hardware. They want to use existing hardware. So I think JP Morgan is notable because they're not only interested in quantum computing and what it could do for banking, but they're also interested in quantum communications. So the theorists on the quantum communications and networking side, I think they have a lot to offer by building protocols. Something that I used to say in some of my earlier talks when I was trying to explain to investors how things evolve in this space is like 3 things have to come together for communications infrastructure, well, communications in general to work. You need infrastructure, so you have to have an infrastructure that can host it. You have to have the hardware, which you can put on the infrastructure to build the network, and then you need the protocols to run all of it. Right now, there are no standards that have been declared by an international community for what the hardware should be or what the protocols should be. So I think that there's a huge opportunity on the protocol space for theorists to work on quantum networking.
There are many more questions, but little time. I will share an invite with you for the Discord group too, Noel, and there you can see all the questions.
Okay. Yeah, I'll try to answer them.
Amazing. Thank you so much for this amazing keynote. And we look forward to take it further on the QKD side in the workshop with QWorld. Thank you for creating the foundation for this, Noel.
It's really, really a pleasure to be here.
For those of you who wondered what is entanglement swapping, that will all be discussed the next days. Let us go through the program a little bit. today, so far, we had a keynote by Worley on quantum computing. You asked many questions. Thank you so much. Amazing session. And now quantum communication. The next 1.5, 2 hours, we will take it a bit more in depth, a bit more theoretical. By QWorld, Aisha Khalik will give the start of the workshop on quantum key distribution, starting with the classical side. And then Gibran will introduce you to quantum computing and programming. So for everyone who just thought in the talk, wow, this went way too fast, we will now go a bit more in depth, a bit more step by step, and you will also get exercises and quizzes combined with the lectures for these workshops. Then many things that Noel just mentioned in the talk will be discussed the rest of this month. For example, what kind of lasers do we need for this? We will have a lab tour by NKT Photonics later in the program. What is the difference in, or how can we protect us with quantum internet versus post-quantum cryptography? Post-quantum cryptography is something that will be discussed more on Friday. And then there were questions about what are the limitations of quantum computers. This will be discussed much more the upcoming week, where we will have a very solid and excited keynote by David DiVincenzo, the inventor of the DiVincenzo criteria for quantum computing. And then hardware lectures on all main different qubit modalities, combined with lab tours, so you can really see what it's like. And the program aims to be for everyone. So for everyone who is starting, there are modules that are for your level. And for everyone who is more advanced, you should benefit a lot from all the different content that is given. And then after this comprehensive program this month, there will be industry projects. We are starting now with Deloitte, with Xanadu, with a national lab in the US, and expanding, where the best participants can join these projects as a launchpad for yourself to enter the quantum space.